cables for VFDs. In a nutshell, it's because of the VFD output waveform. And there's major differences between the utility grid voltage and the output of an inverter. And fundamentally what it comes down to is voltage rise times. Looking at a sine wave, we go from 0 to full voltage in roughly 4 milliseconds. And if you calculate that out, it's 1 volt per microsecond. And that happens twice per cycle, so roughly 120 times per second. So it's nice and smooth. Inverter rise time, however, with IGBT inverters and then the other modern switching technologies, the rise time is in the order of thousands of volts per microsecond, and it happens at the carrier rate, which is 1,000 to 15,000 times per second. So as you can see, the waveforms are substantially different, and that places different demands on the power cables. We can split the impacts of this into 2 groups, immediate impacts and long-term impacts. Immediate impacts include transmitted electrical noise, which interferes with low voltage signal cables, sensors, radios. This is mitigated by using shielded cables and proper grounding techniques. You need a good understanding of your facility's grounding system and strict compliance to terminating the shields correctly in order to minimize the noise. Basically, there's 3 approaches to shielding. A foil mesh drain wire configuration performs very well for low and high frequency shielding. Copper tape is less efficient at containing lower frequencies, and it can gap at bends, providing free space for noise to exit. Armored cable provides excellent shielding over wide bandwidth. One thing you have to make sure is that the armor is not grounded along its run to the motor. So for noise containment, the best choice would be armored cable, followed by a cable with a foil mesh drain wire, then followed by copper tape. And I can't emphasize enough, you need to follow established grounding practices. If not, really all you have is an expensive motor cable. Now, ABB has published an excellent paper on grounding techniques for drives, which I'd encourage you to read up on. Now, let's discuss the potential for inverter tripping or performing erratically. There's a capacitance between the wires coming out of the drive. So whenever you have 2 conductors at a different potential, you're going to see a capacitance. Now, with motor cables, that capacitance can range anywhere from 50 to 150 picofarads per foot. So with long motor leads, so say we have a 100-foot run, you may see a peak current of 1 to 1.5 amps out of the drive just charging and discharging the cables. So, and with even longer runs, that current can actually interfere with the drive performance. And in some cases, the current can exceed the instantaneous overcurrent trip of the drive. Now that's more prevalent on smaller inverters. So if you have a 3 horsepower, 4 horsepower, 5 horsepower drive, you really have to consider this if you have a long cable run. Some tips to keep the cable capacitance down, keep the drive as close as practical to the motor. The other thing is to use motor cables with a greater than 20 mil of XLPE insulation. XLPE insulated cables have lower capacitance and therefore reduced charging currents. Now, if your cables are already run and you're experiencing issues due to this capacitance, you really have no other option but to install a filter at the drive. So to summarize, locate drives as close as possible to the motor. Use a 1,000 volt rated cable with a greater than 20 mil XLPE insulation. And for shielding, foil mesh drain wire shield. Now, let's talk about some of the long-term effects of the drive waveform. They include motor cable degradation, motor insulation damage, and motor bearing damage. The waveform's fast rise times result in transmission line reflections, okay? And essentially what that can do is it can double the voltage coming out of the inverter for very short durations. But those spikes can exceed the corona inception voltage of PVC. Now, if there's air present, and just through manufacturing processes, there's a potential, you're going to create ozone. And ozone will degrade PVC and potentially to the point that the cable has a failure. So that's the reason why most VFD manufacturers recommend using XPLE with a minimum of 20 mil thickness. XPLE has a higher corona inception voltage. Now, if you have a motor with insulation failures, you're probably going to need a terminator at the drive or at the motor. Most new motors are inverter rated, and pretty much the first turn failure of insulation has been eliminated. Now, bearing currents are a different story. Bearing currents over time will cause pitting of the bearing race and ultimately can result in failure. This is a phenomenon called fluting. And here's a sample picture, but if you look online, there's many pictures available about how this issue presents itself in the motor. Now, I've seen personally more issues with bearing currents than I have with motor insulation failures. Bearing current is caused by transient common mode voltages, and you can minimize these voltages by keeping the ground impedance of the system as low as possible. So to combat common mode currents, there's no real clear standard from manufacturers. Cables with segmented grounds are referred to as symmetrical or balanced cables. The symmetrical cables, what they do is they include 3 ground wires with each of the conductors, and they're wound in a way that it promotes equal coupling of high frequencies to ground in each phase, from each phase. So at the end of the cable, you have a minimized common mode voltage. So segmented grounds would provide the best performance. This chart from ABB shows configurations and performance. My takeaway is that the best technical choice is armored symmetrical XPLE cable, followed by shielded symmetrical XPLE cable. Now, one thing to keep in mind is that the next generation of inverters are going to have even faster rise times of voltage on the output. So paying attention to noise issues and potential cable insulation failure issues now will protect you down the road. So here's some basic rules to follow. Use symmetrical XPLE cables, minimize the length of exposed cable after the jacket is removed. Ground shields, drain wires, and ground leads at both the drive and the motor, which is counterintuitive to some of the other noise suppression. When you have a shield, there's always talk about ground at one end only because you'll create a ground loop. In this scenario, you want to have a solid ground at both ends. Don't ground armored cable at intermediate points along the run. Avoid long parallel runs of control and sensor wiring and the motor leads. If they ever do have to cross directly at a 90-degree angle. That's going to prevent noise from being coupled between the 2 cables. And always use a conductive gland at the motor to provide a 360-degree shield ground. Now,